Hi, welcome to this lesson on Euclidean geometry, the Pythagorean theorem. Let's have a look at question 5. In the diagram, we have that xz and wz are tangents to the circle. So that's really important that they are tangents. Okay, and they meet at a common point z. So automatically from one of our tangent theorems, we know that these two side lengths are equal. We're also told that angle xyz, so this angle here, is a 90-degree angle. So by virtue of the way this diagram is constructed, this would be a right angle, that would be a right angle, and that would be a right angle as well. So we want to prove that xy all squared equals oy times yz. So again, when you see a problem like this, where you want to show equality of side lengths, it usually stems from showing some sort of proportion. And the proportions come from similarity in triangles. We could rewrite this and just say that that's xy times xy equals oy times yz, and then if I decided to divide both sides by xy, I'll get xy equals, so I divide one of the xy's out on the left, I have oy times yz over xy, and then I could divide the yz out on the right hand side, so I'll get xy over yz equals oy over xy. So if I can show somehow that proportionality is equal, that is true, then I can just rearrange the equation like I've done here backwards, and that shows that xy all squared is equal to oy times yz. Okay, so you can always try work backwards when you have a square term to see what kind of proportion you need to work out in the long run. So immediately, I'm looking for two triangles that uses the side length xy in both the triangles. So xy is this length, is this side triangle here in purple. So I see two right angle triangles. I see this triangle here, which is given by OYX, and then I'm also given this other triangle next to it, which is this triangle XYZ. Okay, so if I can show that those two triangles are similar to each other in a specific order, then I can use this proportionality to try and derive this equation that I want here. Okay, and the equation actually kind of guides you into what kind of similarity you want to actually prove, right? Because it tells you there in the relationship. So if you're doing xy to yz, it almost looks like xyz as the one triangle. And you kind of want to show maybe that that's similar to another triangle, oy and xy. So let's see, if we went in the order xy over yz, then we want the order oy, right, over xy can be rewritten as yx as well, okay, because xy equals yx. It's the same side length, right? It's this side length here, regardless if you change the letters around. It just denotes the same side. So there it is. That is the proof we need to show, is that those two triangles are similar. Okay, so this is how you can sort of work backwards to kind of see what triangles you need to show are similar. So proof. I'm going to say consider these two triangles. So triangle XYZ and triangle OYX. I'm going to show that these two triangles are similar, and I'm most likely going to use angle, angle, angle. So firstly, I note that angle XYZ equals 90 degrees. That was given to us. XYZ, sorry. Let's put the hat over the right place. Okay, that was given. And then also that angle OYX must be 90 degrees, and that's because angles on a straight line, right, must sum to 180. Okay, so therefore angle XYZ equals angle OYX. All right, so therefore I've shown that essentially these two angles y and y in those two triangles are equal. All right, next, I'm going to rely on the fact that these are tangent lines, this xz and wz. So what I'm going to notice is that angle OXZ must equal 90 degrees. That's because OX is perpendicular to XZ, reasoning radius perpendicular to tangent line. All right, so this entire angle here is 90 degrees. So what I'm going to do, I'm going to say then that this angle x1 here, all right, so in triangle OYX, angle x1 must be 90 degrees minus angle x2. Sorry, that's what I was looking for there. All right, because if you add angle x1 and x2 together, you get 90 degrees. So this equation is true, okay? x1 is 90 degrees minus x2. Okay, so from here now, so if I look at that angle, so that's 90 degrees minus x2, right? x2 is this angle here, so we can just call it itself, angle x2. Then by angles in a triangle, in this larger triangle xyz, this angle here must be 90 degrees minus x2. Okay, so what I'm saying here is that this is angle x, this angle x1 here, right, is equal to 90 degrees minus angle x2, okay, because this entire thing is 90 degrees, so this is going to be 90 degrees minus that other angle x2. So therefore, this angle here must be also x2 by angles in a triangle, because if you add these two together, you get 90 degrees plus the right angle. And the same thing is true here. This is angle x2, so this must be 90 degrees minus angle x2. Okay, so we do have a similar triangle, right, if we look at the ordering here. So this implies then that angle, what's this one here, O1 equals angle x2, this angle here. Okay, and the reason for that is angles in a triangle. Okay, they all sum to 180. And then in triangle xyz, right, angle x2 is equal to itself, right, common angle. And angle z must be 90 degrees minus x2. That is angles in a triangle. So essentially in this diagram, what are the angles that correspond to each other? Well, if I look at these two triangles, this angle x2 here relies to O. So I can say triangle X and then triangle O, those two angles. Then the angle Y's are both 90 degrees. And then lastly, by angles in a triangle, this would be Z and then this would be X here. So I've shown this similarity is true by angle, angle, angle. And that's exactly what we wanted to prove. Okay, so we've successfully shown now that this triangle, these two triangles are similar, and therefore I can work backwards now. So I can say xy divided by yz, which is here, is equal to oy divided by xy, which is this here. So working backwards here now in this if and only if statement, I can work backwards and show then that this statement is true. xy all squared equals oy times yz. Okay, because this is the proportion I'll use, and then cross multiplying gives you that expression. All right. And then lastly, they want us to prove that oy over yz is equal to ow all squared divided by wz all squared. Okay, so at first glance, this looks quite tricky because you might not necessarily have the correct triangles when you try to work it out the first time. I recall the first time I tried this problem, it took me a while. But then I recalled, what have I kept saying when you do a Euclidean geometry problem? Something you've proven before is usually going to be the clue to help you prove the next argument or statement that they're asking you to show. So previously, we've shown that triangle XYZ is similar to triangle OYX. We've shown that. So now we can use this fact and look for another triangle that has YZ, for example, because we've got an OY here, right? We want something with a YZ. Oh, we've got that. Perfect. But now, do we have something with OW? Not in this current statement. Do we have something with WZ? Not in this current statement. So automatically, this right-hand side is the clue to look for a third triangle now, that if we can show is similar to these other two triangles, then we're done, right? Because then we have this long chain of similarity that we can then use proportionalities to try and work backwards towards this. Okay, so what am I going to show is similar? So I'm just going to show one of the triangles is similar to the other ones, because by the transitive property of similarity, if A is similar to B and B is similar to C, then A is similar to C as well. Okay, so I'm going to consider triangle, and it gives me the clue there, OWZ, okay? And let's consider triangle XYZ. Okay, if I can show that these two triangles are exactly similar in this order, and because triangle XYZ is similar to this triangle, then triangle OWZ will also be similar to triangle OYX. Okay, so let's take those two triangles out and analyze them. Okay, so here's X, Y was a 90 degree, and Z. And then the other one, OWZ, is this triangle here. OWZ. Now, OW is a radius line and ZW is a tangent. So automatically that's going to be a 90 degrees. So I'm going to note that down. Angle OWZ equals 90 degrees. And the reason for that is radius perpendicular to tangent line. Okay, so far so good. They both have 90 degree angles. All right. But remember, in this triangle XZY, this was Z1, and then this was Z2. All right, so they're not necessarily the same, right, just yet, but we need to show that they could be the same. All right, so what else can we look for here? Well, I know that since this is a center, O is the center of the circle, that was given to us, right? And chord XW cuts that center. This means that these two sides are bisected, so they are equal in length. We know by the tangent theorem at a point, these two side lengths are equal, and here we have a common third side equal to itself. Okay, so here we have sides that are, so these essentially what we've shown here, three sides are equal in that order, so those two triangles are congruent to each other. Right, so I'm going to make a side note here. Triangles XYZ is congruent to triangle WYZ. Okay? And that again is by side, side, side being equal to each other. And again, to reiterate, why are the sides equal? XY equals YW. Okay, and that is because line from center to chord, perpendicular line rather, from center to chord, bisects the chord. Okay, so therefore those two side lengths are equal. We know that ZY equals ZY, common side equals to itself, and XZ equals ZW, that is from tangents from same point. Okay, the same point Z that they are originating from to the circle. So that's why these two triangles are congruent. So therefore, I can conclude that angle Z1 equals angle Z2. So these two angles are equal. And that helps us because that's what we needed to show for similarity. So therefore, these remaining angles by angles in a triangle must be equal to each other. Okay, so let's put that all together. So I can say lastly, angle, in this case, O2, right, must equal this angle X2, okay, by angles in a triangle. So therefore, triangle OWZ is similar to triangle XYZ. And by extension, since triangle XYZ is similar to triangle OYX. So I've got this triple similarity here. Okay, so again, to reiterate, why did I need to do that? Well, that's going to allow me to use all these different side lengths in a proportion that will hopefully get us to this here. Okay, the OY and YZ comes from these two triangles that we showed similar previously. But to get OW and WZ, we needed a third triangle introduced to create this proportionality. Okay, so now let's check what proportionality do we need to use in order to achieve this equation, this equality here. Okay, so first of all, if I go back to my previous question, because there's squares here, it's hard to get multiple squares popping out everywhere. But in the previous question, we proved that xy all squared equals that. So I'm going to start that as my base. Xy squared equals OY times YZ. And again, the motivation for doing that is twofold. One, this has two squares here on the right. So I needed something originally that had a square already to help me. The other motivation was that we have OY over YZ, and this one has OY times YZ. So that's even more motivation to use this equation. Okay, so when you get questions like this in a test or exam setting, the words that usually follow a question like this would be hence or otherwise prove. The hence is a big clue to tell you that, hey, something you proved earlier might be useful to be able to prove this now. Okay. All right, so now that we've got that, what I'm going to do over here is divide both sides by yz. Okay, so I'm going to have xy squared divided by yz equals oy. The reason I did that is because I want oy divided by yz. So dividing it once by yz gives us this equation. And then dividing by yz again. Okay, so it's going to be dividing by yz again. So you're going to have another yz here in the denominator. And on the right-hand side, you're going to have oy over yz. Okay, so on the left-hand side, you have xy all squared over yz all squared equals oy over yz. Now, so far, we've got this left-hand side. But on the right-hand side, we want ow squared divided by wz squared. We've got xy squared over yz squared. So, if we can just show that xy divided by yz is the same thing as ow divided by wz. If we can show that, then if you square both sides, you're going to get xy squared divided by yz squared equals ow squared over wz squared. Okay, so this expression here is what we've got already. So I can replace it with this, and then that will complete the proof. Okay, but now how do we show that that is the case? Well, what did we just do? We proved a triple similarity and we haven't used it yet. Okay, so in that similarity, I'm going to show that if you look at xy over yz, so essentially in this triangle here, xy over yz, then in this order it must be ow over wz. So it must be ow over wz. And we're done. Because now if I square both sides, I'm going to end up with this right-hand side expression here. And I can plug it back into this. Okay, so this was quite a long one, but the main takeaway from these problems is that mathematics is not done in isolation. So whenever you're doing a problem, it's usually linked to something you've already shown. Okay, so always keep that in mind. Awesome. I'll see you in the next one.